Hello everyone and welcome back to the course. I'm taking over from Juan. My name is Arno and we will have a look. So first of all, let me check just to make sure that everybody can hear me. Testing, testing. And also, if you can let me know whether the size of the Jupyter Notebook text is large enough for you to be able to see. So, in other words, the text there, if that is big enough or not. Okay. Okay, so it may just indeed be and since there's only 3 of us, I will wait just a minute for Luke to restart his browser. Ah, okay, great. So you can hear me now as well, Luke. Okay, great. So I was just wondering if the text that I'm sharing, if it's big enough. I mean, I can always make it bigger, but so these commands here, are these a little bit too small to see, or is it just about doable? Okay, great. Thanks for confirming. I'm just going to close something because it's jumping around. There's a notification in the bottom, which I think is kind of distracting. So just give me a second. Okay, so Juan told me that the session in the morning finished with the looking at the episode 3, I think it's called, looking at the plotting challenge, but maybe not quite going through the plotting challenge. So I thought it would be useful to just have a look at that. Maybe you had a chance during lunch to try this yourself. Show the solution. Well, we'll go through the solution basically, but let me just load up. As usual with these carpentry style sessions, it's the live demonstrations of somebody like myself typing stuff out, and it gives you the benefit of seeing all my mistakes, and that's part of the learning from. So I'm sure there'll be stuff that doesn't work. So I'm just going to load up the data that is necessary. Okay, right. So I've just skipped to the very beginning where we actually load that initial survey data, which you should still have loaded in your Python session. And then let me see if I can skip straight to the challenge without having to initialize anything further. If it doesn't work, we'll work out why it's not working. So the challenge down here, these 2 plotting challenges at the end. The first challenge was to create a plot of the average weight across all the species per site, i.e. per plot ID. So the idea there is that we're doing one of these grouping operations. So we want to group our data according to the site. Yeah, and this. So here we go. So the site was the column ID corresponding to plot ID. So first of all, I'm going to create a here we go. I was using PD instead of DF. So just going to correct that. Data frame. Don't know what I was thinking there. So the data frame, I'm going to group that by what? I'm going to group it by the plot ID. The thing with these things, all these groupings, is the first instinct. Well, when you're trying something for the first time, also to see, okay, what does that actually look like? Can I just give me the data? But unfortunately, these group by functions are kind of logical operations that set up the gathering of the data according to certain keys as you specified, like in this case, plot ID. But you actually then have to go on and do an operation like telling it to get the mean, or to find, if you do describe, that you can get all the stats out based on that grouping. In other words, it's grouped it according to the plot IDs, which range from 1 through to plot ID 24 for the 24 ecological survey sites. But the thing we care about is the mean. Okay, yes. What I need to specify is what I want the mean of first. And the thing I want the mean of is the weight. So again, just asking for the weight itself still doesn't give me, the grouped weight. It's the group by construct just gives me something that sets up the data to get statistics out according to this grouping based on plot ID. So I'm going to ask for the mean of the weight grouped by plot ID. And you can see on the right-hand side here, that's the first part of that line towards generating the plot. And all I'm left to do then is to either in a new line, or I'm just going to modify this. Well, I'll just copy that same expression, and dot at the end, actually go ahead and plot it. And the kind of plot that we've been doing so far is a bar plot, and that is what we want. Okay, so that looks like what we're wanting. So that was a fairly straightforward thing. We didn't need to do any kind of unstacking. So I think unstacking and stacking is covered. Will be relevant. Yeah. So unstack comes in. So unstacking comes in the next bit. Yeah, we'll talk about it in a minute. But the unstacking is not relevant here, not needed here, because it's essentially the unstacking is a way of undoing or flattening the multidimensional organization of data based on hierarchical grouping. So just now we were grouping the survey data purely according to one key, the plot ID. But if you group it according to more than one key, then as we'll do in a second, then yeah, you have to do some flattening of the data in order to be able to actually plot out what you want. So we'll get to that in a second now, which is first of all, if there's any questions about the first plot, feel free to, if you have any, or maybe if you have another solution, a different approach that you're wondering whether that works or not. So this kind of doing it in one line, works. If you want, you could make your code potentially more readable by saying something like, defining an intermediate variable site mean weights to be equal to that well, let's just, or that just, you could say, like, if you wanted to, you could define something called site weights. Let's say that it's equal to, well, site weights by plot. You know, if you want your code to have some intermediate variable that actually makes it potentially easier to come back to later, to have the logic inherent in the intermediate variable names. That might cost you a little bit more performance potentially. It can do, because you're explicitly creating a new variable to store the result of evaluating the right-hand side. Whereas it's possible if you have a single line with all the steps in one go, including the plotting. Then, whereas some intermediate intermediate data structures are still sometimes created and stored explicitly in memory, sometimes that can be done more efficiently, so that that can be avoided. So it can be the case that explicitly defining, this additional variable could potentially be less performant. But you can always use, actually, when it comes down to it, if this is something that matters, if this is not just something you're doing interactively to play around with your data, but if you're doing something batch processing, then you can always time the time taken with different options using the time it command. And we'll look at that in a couple of cases, how to use the time it command to figure out what's faster if you've got more than one option. Anyway, so yeah, you could define this new variable site weights by plot, and then clearly you could define another intermediate one to get the result of the calling .mean on that, and then again actually plot that. Plot is slightly confusing here because I prefer site, because even though the key in the data file is plot ID, since we're talking about plotting plots, it can all get a little bit confusing. So purely from the perspective of clarity, you might want to call it by site, and then know that relates to plot ID, the data. Anyway, enough of that. Now let's go on to the second plot, which is this plot of the total number of males versus the total number of females for the entire data set. Okay. So what are we asked to do? We're asked, we need to create a grouping again, grouping by one of two values. So let's create intermediate variables just to be very explicit. So we say, so we want to group by the sex in this case. Okay, I'll type it out instead of copying and pasting, because that's the right thing to do. Take our data frame, group by sex. So that's just a logical grouping. And then we've got there's more than one way of doing this. Yeah, the example solution here suggests that you count the grouped by data. So count, if you remember, it's just one of the statistics that is available, right? If you ask describe, which gives you all the statistics, you'll see it's got generates the count, generates the mean, generates the standard deviation, minimums, percentiles, etc., for all the different columns. But now we're asking just for one metric. We're asking for the count metrics. As we'll see a bit later on, one of the later episodes, there's some question here regarding nans, whether values whether it includes cases where there's no data available for the field in question. But we'll look at that later. So the conclusion here is that, in fact, maybe you can already see it. Yeah, you can already see this coming out here. So we've asked pandas to tell us to do count for these different, well, to do count on the data in the survey's data frame grouped by sex. And what is it counted? Well, we've not restricted it any further. We've just asked it to do the count grouped by sex. And what data is there? There's a record, there's the month, the day, the year, plot ID, species ID, hindfoot length, and weight. So all that data is there, and it's doing a count grouped by sex for each of those fields, right? And you can see here for record ID that it's 15,690 for female and 17,348 for male. And then it's 15,690 is the same for record ID, it's the same for months, same for days, same for years, same for plot ID, same for species ID. But here, when it comes to these two values, hindfoot length and weight, they're suddenly different numbers, not 15,690, but a lower number in each case. And similar probably here for the males, so 17,348 in total, and that is the case for all of these columns, apart from these latter two. So that's actually because, as we'll see later, these the count is actually counting non-null or values that actually are not values that are actual genuine entries, that are actual numbers. So what basically is what will end up being the case, these measured things like hindfoot length and weight, in some cases for some ecological survey data, clearly there were no measurements made. Therefore, some values are not numbers. They're not recorded as genuine values. And so when you ask pandas to count the number of entries, it skips those and ignores those. That's why the total number of entries that it arrives at by counting is lower for hindfoot length and weight, where there's some missing values, than it is for the record ID, which is simply unique. You know, the record ID is a canonical thing to go by, because no matter whether you do or don't measure a weight or a hindfoot length, apparently there is still still a record. Anyway, that tells us, that gives us the count, and then what we want to plot. We want to plot that basically, right? Yeah, so we have to choose which one of these things to plot, which one of these totals to plot. Well, let's go by the record ID. We could have chosen any of these first few because we see it's all the same value. So we just have to choose one of them. So we'll choose record ID for the reason that I just gave. First of all, that just focuses in on the record ID, and we ask it to plot that again with kind equals bar. Okay. Now I'm just going to try a slightly different formulation. So let's see. Here we had, yeah, okay. So what we did before was we said group by sex, and then we asked it to count, and then we honed in on the record ID, right? Let's see. We can, of course, could have honed in on the record ID first, I think, and then asked it to count. That's ultimately selecting the same data, but logically, the order in which you're asking pandas to narrow in on the data is different. So before, we asked it to count everything, and then selected out of those results from counting, we asked it to select the values for the record ID column and plot those. Whereas in this option, we're not asking it to count everything. We're saying already hone in on purely the record ID column, and then just count the record ID column. And so we get the same result. I mean, if it's not already, if it's not already apparent from the values themselves, then it should be clear visually from the two plots. But going back to what I said about performance, if this is the kind of operation you're doing many times, and you maybe not plotting it, but let's just say you're just generating these values, right? So I'm just going to remove the plot commands from both cases. So here, the two alternative formulations give you the same answer. We're going to use a magical command called timeIt. I say magical. That is actually not just my term. It's the timeIt command is not generally sort of valid core Python language syntax. It's a special term that is recognized by the IPython and Jupyter Notebook versions of that wrap around the Python interpreter. So they provide some additional functionality that is kind of like your IDE sort of development environment or IPython environment functionality. So it's a little bit of a meta thing. So it's not Python syntax, but it is usable to do what it does, which is to time a command or a sequence of commands. So the simplest way to use it is on a given line, simply say time it, and then give, and then space, and then the thing you wanted, the line of code you wanted to time. And okay, I'll just launch that. So just say execute, and it takes a while. Not that long, it takes a while. And what it does is, it doesn't just run that code once and then see how long it takes, because it takes so little time that it's very inaccurate. So what it does is it runs it a bunch of times. It decides based on some heuristic how many times to run it. So here it's decided to do 7 runs with 100 loops of the same thing each. So it's actually done 700. It's actually run that line 700 times, calculated mean and standard deviation, and it gives you the timing information about how long it took, 2.41 seconds with a very standard deviation, 23.5 microseconds. Okay, fine. Is that relevant? Well, let's time the other alternative formulation that gives the same answer. Let's see what happens. Okay, so that's nice. So this is faster. It's about twice as fast. It's decided to run. You can see it has some decision heuristics time it to decide how to time the thing. So it's decided to time this line of code by running it more times, probably because it tested running it once or a few times and said, oh, it takes so little time. It's below some threshold where I need to run it more times in total to get good statistics, given some overheads of timing. So anyway, if you take these values, if you take them at face value, what this is saying that basically, if you were honing in on doing this computation, and it was something where performance mattered, if you're doing it in a batch process, analyzing loads of data, and you're doing it gazillions of times, then if it's all the same to you, just use this formulation rather than this alternative formulation, because it's about twice as fast. And why is that? It's basically the clues in how I explained the logic of the two formulations. It's that you're just asking pandas. You're narrowing down on the data you're asking it to operate on more narrowly. So, like I said in the first formulation, you were asking it to count everything, all the data, and then select a subset of those results. Whereas in the second formulation, you were telling it already which subset you were interested in, namely the record ID. So that's just one. Well, what data type is it? It's a. If we ask it what is the type of that, oops. Right, it's a group by on a pandas series. Anyway, don't worry about that too much. But it's the basic principle is that you've just narrowed down already data on which you're asking pandas to operate. So that's a general principle. So to keep that in mind, if you've got, if there's more than one way to do things, experiment around with it and try to narrow down what you're asking pandas, or actually really any Python code. Could be any other library or just some Python code that you yourself write using lists or whatever from NumPy arrays. What you're asking it to operate on. Okay. So yeah, let me see if there's any thoughts or questions at any point. Just feel free to pop it in the chat, or you can even unmute yourself and unmute your mic if you like. But I'll go on to the next plot, which is this stacked one. Okay, stacked bar plot. Stacked meaning it'll look like this, right? Where we're summarizing the weight and the stacked variable being sex. Okay, so we want up with a plot where essentially we end up skip to what we're so visualize what we're looking for. You know, if you go at something like this, you want to visualize what you're looking for. And this is what we have in mind. What we're going to aim for is that you've got for each bar, it's stacked in that the value of the weight for the males and females are stacked on top of each other for each plot ID. So just to talk through the logic, it explains the idea of how the plot command deals with data where you're asking it to stack what it expects to get in. So the example it gives here is that you define the data that you want to plot as a data frame here. And we'll see that basically we're going to get our logical selection of what we want to plot into a similar format as this, where we've got two categories, things that are in this example, things that are 1 and 2, or A, B, C, D. And what our question is that we've got two categories. They're not there. What they actually are the sex and the site, the plot ID. So what we'll see is if we follow this logic, so we want to group the data by plot ID and by sex. So I'm not typing this out completely, but you can see where I copy pasted it from. So grouping the survey data by site and by sex is as follows. Okay. Then what we want, I think this is misnamed because it says count here. I would call it something else. So once we've grouped the data by site and by sex, so I would call it weight by site and sex. Total weight, if you want to be really explicit, right? That is what it's asking for. So it says here count, but we're not asking it. What is it counting? It's counting the weight. So I'm just calling it something else, this variable, rather than an example, which I think is a little bit misleading. So we've grouped our data by plot and sex, and then we're asking it to select the weight out of that and sum. This is better than telling it the sum and then selecting the weight, because the same logic as I showed just before. You know, it's, you're sub-selecting the data to operate on and then asking it to sum. Okay, what does that look like? We should be able to get something out now, because it's no longer simply a logical group by construct of the data. We've actually told it to do a sum and give us a metric out, an operation, statistical aggregation operation on that grouping construct on the data. So here we get this kind of hierarchical two-level hierarchical results. So plot ID, and then for each plot ID, subdividing into M, F and M, F and M, F and M, and then the value for each of those is the total weight that we want. Now, the unstacking thing that I mentioned before comes in if we want to actually plot this, because what we want to do is we want to basically get this into a form that looks like this form. So whereas the form we have is one where you've got this kind of, I said flattening, but actually it's unflattening. So basically you're unfolding. What you want to do is you want to unfold the two dimensions that are sort of here as two columns into rows and columns. And that's what the unstack command does. So if you look at the next step, if we take total weight by site and sex and we say unstack, not underscore unstack, dot unstack. That's what that does, right? So it, as I said, it kind of unfolds the nesting, the two-level nesting that's captured in two columns, and folds it into column and row, so that you've got the rows corresponding to the plot IDs and the two columns corresponding to the sex. And now we can go ahead and plot that. So we want to say that dot plot, and we tell it stack is true. Right, so I've just taken the plot command, for plot stack is true with an appropriate title, and added that on to the result of doing the unstack on the result that we had. So that works, and then it adds, next steps are here. You can add the label. We add label for the X and Y axis, but I'm going to skip doing that because I think that's clear. Okay, right. I appreciate it took quite a bit of time to go through full detail, but I thought it was useful to go just explain that very explicitly, and then that'll set you up hopefully to deal with similar plots a bit more quickly in future. So I assume that Juan will have gone through the conclusions, or maybe the conclusions from the episode are clear already, so we can use a group by functionality to organize, to create queries on the data. Right, feel free to post any questions. Meanwhile, I'll continue on to the next lesson, or I should say the next episode, which is, let's see, lesson 4, indexing, slicing, and subsetting. So we've got, what's our schedule? Okay, so we've got, we started at 1, we've got until 2 o'clock, so let's see how far we get in this episode. I will just create a new kernel for this. Okay, and I will call it for slicing, indexing, slicing, subsetting. Okay. So, what's the idea here? As it says here, how can I access specific data? So we're essentially going to look at selecting subsets of the data. So far, we just we did logical groupings to organize the data, but we still were dealing with all the data and doing metrics, aggregate statistical metrics on all the data. So now we're getting into something that you often want to do, which is, select a subset of the data, and we'll look at various ways of choosing subsets. Okay, and those methods are indexing, slicing, and subsetting. So feel free to follow along. So I'm going to import pandas SPD surveys data frame equals pd.read data. I don't know if anybody has been using tab autocomplete, but this is quite useful in IPython or Jupyter Notebooks. So I started typing that and tab. Ooh, lots of options here. Tab autocomplete. I know it's in data. Yeah, and then what have I got in there? Tab, tab, tab. Surveys. Plural.cv. Okay, of course I left out CSV. So, okay. So, yeah, so we'll look at different ways of selecting subset of data. So indexing, so we've got, you've already seen that we use, I think you've already seen we use square brackets to select the subset. Maybe not, but anyway, this will show that here. So what is all our data? If I just take the head to show the first few entries, this is some familiar data from before. So what I can do is I can ask it to tell me, to show me all the, simply show me all the, only one particular column, like the values stored in the species ID column, right? You might ask what kind of a thing is that? So the surveys DF is a data frame, and if I ask it to give me the entries corresponding to species ID, that is a series. So pandas series is a panda data object, data structure. That is so series is basically like a like series of numbers that can make, and different, you can combine series to make up a data frame. So often when you extract, when you extract a column from a data frame, what you get out is a series. You could make that into a data frame with a single column, but then a data frame is essentially one or more panda series with an index that doesn't have an explicit column name. That's just an implicit index. The panda series is kind of like the it's just one column from a data frame. Okay, and another option, another syntax that you can use that is to say name of the data frame and then a dot species ID. So that also works. And I don't think there's any performance difference in using the different syntax. Let's just see. Taking a while to run. That's interesting, actually. Okay, so there is a difference. Okay, so that's something to maybe keep in mind. Yeah, that's nice. See, it always pays to experiment with this stuff. Okay, so yes, it says here. Yeah, so you can take that result and load it into a new variable, and that variable will be of type date panda series, as I said. And you can specify more than one column name. Like you can specify species ID and plot ID. Not like that. Right, what I forgot. See, this is benefiting from my mistake. So what it would accept is a list of one or more values. You can just specify just one literal value, but if you want more than one column label to be selected, you need to give that as elements of a list. And the list is itself specified through these square brackets, right? So that's a list. Yeah. Okay, so so we got both those columns extracted there. And no surprise, if you ask it to give a column a label that doesn't exist, it will tell you it doesn't exist. It'll tell you a key error. So remember, what columns have we got? We could actually, we could enumerate, we could print out the data like we did before, or we can ask it. We can ask for the attributes columns, which tell us, and actually equivalently, you could ask it for the keys. The keys is a function, and columns is an attribute. So if we use start to type column call and tab autocomplete, it'll tell you, it'll tell you this, what you can get as an attribute in the instance. Whereas keys, if you start to auto type and then you ask it to tab autocomplete, it'll tell you F for a function, which tells you that obviously you'll need these parentheses in order to call the function. And okay, so here's a little reminder about how to name variables. Basically, don't use list as a variable name or other reserved variable names. That's simply useful to keep in mind. Okay, so that's indexing. We'll look in a second at selecting. So we used indexing to select specific columns. Now we're going to look at selecting a subset. So here's an example where if you've got the general idea in Python is if you've got a list A here, then indexing into that list starts at 0, which means that if you, well, we'll just try it, won't we? Define A as follows, and if I ask A0, it tells me one I0 is the index of the first value in that list. A5 should complain because A5 would be the 6th value in that list. Index 0 is 1, index 1, 2, 3, 4. Index values 0 through 4 are valid values, and they contain all 5 values of the array, but index 5 does not exist. Similarly, so length A would give the same problem because length of A is 5. So asking it for the element of A with index 5 give you the same issue. No complaint. Now let's look at selecting rows, and we'll start with, maybe counterintuitively, but we started with individual columns, and now we're going to start not with individual rows, but subsets of rows, and we'll see that the case of the syntax for just one particular row is a simple case of that. What I'm trying to say is that you can't, maybe it's counterintuitive, but you cannot just simply say, if you want row 0, you cannot simply say surveysdf 0. That won't work. So we'll see in a second how to do it. But as it explains here, you specify for slicing syntax to give the rows or columns. If we include both row and column specification, it turns into a two-dimensional subset, which we'll get to next. But we're focusing on rows first of all. So if you specify, what you can specify is a range of rows, and the range is used to do that. Uses colon here. So if we do what it says there, to select the rows with from index 0 to index 3, what that gives us is the rows with index 0 and 1 and 2, but not the one with actual index 3. So it's 0 inclusive, 3 exclusive. So it includes, this range specification includes the index, includes the row with the first index value, but stops before the row with the final index value. So that's just something to keep in mind. So logically, how would you select? Maybe this seems annoying because could you not simply do surveys df0? You show that it just doesn't work. How do you therefore get just row with index 0? You select the subset of rows which start with 0 and end with row 0, but which is denoted by saying that the final value in this range is one more, i.e. 1. Right? Similarly, if you wanted to select row with index 1, you would select from 1 up to excluding 2. That's a little bit arduous, maybe, compared to maybe simple NumPy arrays, which you would expect. But yeah, that's how data frames work. So example here is some other more syntax, and this is very much analogous with how slicing works in NumPy arrays, which you might be familiar with. Or if not, this is a useful way to learn it. And then once you deal with NumPy arrays, then this will be familiar anyway from these pandas data frames. So this, what we can do is we can say surveys df nothing as a starting index, and then 5. And what it does is it takes, if you don't specify anything, then it's implicitly stating start at the beginning, start at the very first value, and vice versa. If you specify an initial value, like 3, 4, and don't specify final value, then it is all values in the range with index starting from that first value up to and including the final value in the data frame, the row with the final index value in the data frame. And if you don't specify either start or stop, it's just everything. It's just the entire thing. So it's just the same as the original data frame. Right? And there's a final thing here, which is this -1, which is so -1 is just a convenient syntax for saying. So what I'm going to do is I'm going to start at -1. So -1 is a way to indicate the final value. So it's saying start at the final value, and stop at nothing. Don't specify, which means stop at the final value. So what am I going to get? I'm just going to get the final value. So that's the way to get the final value. And you can do, it's just counting back from that final value. So if I ask for -2, it gives me the last two values. If I go from -2 to -1, it gives me the second to last value, etc., etc. Okay, so that's slicing. Now let's see how we can modify some of the data in our data frames by assigning values to subsets. But before we do that, as it says here, we have to look at the difference between copying versus referencing. So before going through we can talk through this logic and then see how it plays out, or the other way around, see how it plays out and then talk through the logic. I think that would be my preferred way, because I think it's just easier to start with a concrete example. So, so what we do is, let's say we start with, so we've got our, yeah, let's say, so we have our surveys data frame, and let us create an explicit copy of that. So let's say surveys, I'll call it the same thing that they've called it in the notes just for convenience. True copy surveys df equals surveys df dot copy. Okay. Now, they should basically be the same. So what that does is it creates a true copy, which means that you've literally taken all the values that are stored in the surveys data frame, allocated a new space in memory, and made all the values in that new space in memory be the same as the values in the space in memory that where the original surveys data frame was stored. And so now you have two spaces in memory, both of which happen to store identical sets of values, because to begin with, at least, because you made an explicit copy. So what that means is, if we go ahead and do something like modify either set of values. So let's see if we. So I'm going to contrast this with the case where, instead of, before I modify any values, let's set up basically like they do is set up the case where you say you define what's a false copy, in a sense, of the data, of the survey data frame, which they call ref surveys data frame, and say that is simply equal to surveys data frame. So we're not using a dot copy, we're just saying equal to. And as we'll see, that essentially creates not a new set of values stored in memory, which are identical to the ones of surveys data frame, but just creates a pointer essentially kind of at the same set of values. Now, why does this matter? This is something to keep in mind, because you can do as follows: you can modify your surveys data frame and say that, like it suggests here, what are we going to do? We're going to assign values to a subset of rows. We're going to take rows 0 through 3 exclusive. Let's see what they are right now. Right, that's what they are, and we're going to change them. So we're going to say they are equal to 0. Right, let's see what surveys df rows 0 through 3 look like now. I don't know why it's skipping back up again. So we've literally just mixed or nulled all these values in every single column, so that assignment 0 through 3 equal to 0 is shorthand for setting all the values everywhere in those 3 rows to 0. So we've changed the original sets of values stored in memory that correspond to that service data frame. Now, if we look at the copy, the so-called copy, the false copy of the reference survey data frame, and we look at the same rows, they're also 0. So essentially what's happened is we've said, like, it's like you had your initial surveys data frame, which is, let's just call that's A, and then we said B equals A. B is our ref surveys frame. You modify A, and that actually means that B changes as well, because B is just a reference to the values in memory stored for A. So that can catch you out potentially. That's why true copies are important, because if you look at the true copy, rows 0 through 3, those remain unchanged. So those are still the original values, right? So that's the difference between copying and referencing. And that's basically what this part here explains. That's something to be aware of and keep in mind. Okay, so now we get into syntax for getting pandas to select not just a range of rows or individual columns, but kind of subsets using both of those. Okay, there's a full range of syntax that we can use for that. So there's 2 approaches that we can use. One of them is based on integers, in the integer indices for both the rows, which is already familiar, which we were just kind of using, and for the columns. So you would specify the column IDs whenever you use this iloc approach. You specify the column IDs. You're also using numbers, not using the labels like record ID, plot ID, etc. that we did as we did earlier. With the location approach, loc approach, you use the label approach for both columns and rows. So what does that mean? So if we look at this first approach, which is based on integers, integer indices, let's say service data frame .iloc, and then we're going to specify a subset based on specifying slicing a range for the rows and slicing a range for the columns. For the rows, we're going to look at rows 0 through 3, 0 inclusive, exclusive 3. And the columns, we're going to look at columns 1 through 4 exclusive. So just to remind what the full data frame looked like, all the columns, all the rows, sorry, the first few anyway. When it comes to the columns, you can see it's chosen the columns with index 1 through 3, because just like rows, the columns indices start at 0. So record ID is column index 0, month is column index 1. So column index 1, column index 2, column index 3, month, day, year. Those are the columns that we've selected using integer indexing. And as before, row 0 through 2 inclusive with this syntax. Okay. Yeah, that's what it says here. Now let's look at the other approach using the location command. What does that do? So what we do with there is, if we, I'm actually gonna, let's take a slightly different. Rather than doing exactly what it says here, let's see how to replicate what we just did using the location, using iloc, but now with loc. So now we want, we can still use the this will still work, 0 through 3. The meaning of how this is, oh, I forgot to actually say it, give the lock command. So it's a dot lock. The way that the 0 through 3 is interpreted is logically slightly different from when you use ilock, but effectively it ends up resulting in the same thing, as long as the indices in this column match the what are numerically sequential, which is typically the case. See some cases in the lesson on joining data frames where that's not necessarily the case, and you need to reset indices when you're combining data frames, but that's for later. So okay, 0 through 3. Well, let's see what happens if we just do that. Okay, no, I said it's the same, but clearly it's not quite the same, is it? Because unlike the ilock case, where if we specified, didn't need to specify the columns. If you leave it out, you just get all the columns, right? That's what that's essentially done here. But so where with the ilock case, when we said 0 through 3, we got the row with index 0, the row with index 2, 1, and the row with index 2, but not the row with index 3. We stopped before that. But now we also get that row. Why? It's because of this difference in how this is interpreted. Because here, the lock location query, how that interprets this range of 0 through 3 is give me all the rows where the index is equal to the values 0, 1, or 1, or 2, or 3. So it expands this, and it tests whether the value of the index in each row is equal to that, rather than simply using them as logical integer indices. So it's simply effectively the difference is that now it's inclusive of that final value rather than ignoring it. So anyway, if I include the specification, if I want to include a specification of the rows I had before, I would now do. So I could now no longer do this integer-based specification, because if it checks whether any of the labels for the columns are equal to integers, that's never the case. I have to actually specify the labels, which is maybe generally what you would want. So what we have? We had month, day, and year. Okay, so that gives me back the same result as I had with the ilock case. And I think that also covers an understanding of the same questions as are covered here. The only difference that we haven't really talked about yet is this case. So this highlights something about the syntax, which is rather than having so for the columns here, it's simply all columns. We don't restrict the subset. And for the rows here, we've specified not a range from, say, 0 to 3 or 0 through 3, 5, 5, 4, 9, but we've given a list with a couple of particular values. We've said give us the rows where the row index is equal to 0, where the row index and the row where the row index is equal to 10, and the row where the row index is equal to 3, 5, 5, 4, 9. So what we get that. Okay, I think it's that. Yes, I think they made a small mistake there, because there is no. I mean, it should get a key error, because there is no 35549. There's only 35548. Okay, so it's now 2 o'clock. So in the schedule, I know listening to somebody talk for an hour can be a bit draining. So we haven't gotten to a challenge yet that you can try yourself. So I will stop now. We'll have a break until 1:15, and I suggest you have a try during the break and into for the first 5 minutes at least, so until 20 past, say. We'll look at this challenge. Just a chance to grab some coffee or no break or anything. Okay. Right. So yeah, so I've tried a few things here, but I'll get onto that in a second. So, okay, so this challenge, there's a summary here just about this challenge, which gives you a rule of thumb, a way to just kind of remember when you might want to use iLock and when you might want to use lock. So it's asking you to try a couple of things here and to see what happens. Okay, so when we ask for this, well, this is basically what we looked at before. Let's just look at the summary. This here is not actually what it's asking you to do, 0 through 3 instead of 0 through 1. 0 through 1 is the case that we looked at before. It's a way to get out simply the first row, right? 0 through 1 exclusive. So it's just actually, it's what you get, what you thought you would get if you did asterisk for just 0, which gives you key error. This one gives you starting at the very beginning, so row 0 through 4 exclusive. So it gives you rows 0 with index 0, 1, 2, and 3. Example, somewhere here. Oh, for some reason these don't agree. Yeah, this is through 5, but here's through 4, so these don't agree. But if it's through 5, then you get rows with 0, 1, 2, 3, 4. This -1 here, so it's starting at the beginning, the first row, all the way through to the second to last row. Everything except the final row, because it's exclusive of the stopping index, and the stopping index is the index corresponding to the final entry. So it's stopping before the final entry. Okay. Then so that's all with this syntax. And then when you use the iLock syntax, then this is iLock 01 gives you the same as simply using direct square brackets. iLock 0 will work with returning the first row. So, and here it's basically the equivalent to all columns, because we don't specify, we don't restrict the columns, the first 4 rows. I can see why. Okay, 0, 1, 2, 3, 4. Yeah. Okay, so it's kind of equivalent to specifying simply with square brackets directly. Here again, you're just restricting now. There's no difference between saying there's 0 through 4, whereas leaving it empty, the starting point, because it's, if you don't specify it implicitly, it is 0. But you're doing here in this case, compared to above, you're saying not all columns, but columns 1 through 4 exclusive. And this one will complain. Because in this case, okay, so these are all iLock, but this one is lock. So with lock, it's not expecting integer specifications of indices, but expecting labels. So it will check whether the index labels correspond to these integers, but it will try to see if, it will check if the row, the start of row, like the row index corresponds to these label versions of the integers, which they do. But it will also try to see if the columns, which columns correspond to literally being labeled as 1 through 4, but none of the columns are labeled numerically. They're labeled with things like record ID, and month and day and year. And that's why you'll get this type error. The third question, how are the last 2 commands different? Well, that's what I've just said. It's about labels versus integers. So just going back to it's actually just another perspective on the syntax. So there's a third option which they don't really discuss here. I don't know why, but it's an option you can use, an approach you can use for subsetting, and it's one that I've taken here. So selecting the rows 1 through 3 exclusive, i.e. the rows 1 and 2, with the column record ID. I can do it as follows. I can say, give me the columns with labeled record ID, and then out of that, give me the rows with index 1 through 3. That's the result. Alternatively, I could have switched around. I said, well, give me the, out of the rows 1 through 3, give me the columns that satisfy record ID, right? It's just another way of specifying the exact same thing. We're compared to the lock format would be to say, okay, lock 1 through 2 and then record ID. And if I use ilock, I can do it by specifying 1 through 3. With lock, you use 1 through 2 because it's where the row indices are equal to 1 and 2 and 2 inclusive. With ilock 1, 2, 3, where it's exclusive of 3, and then I specify the integers corresponding to the, basically this is just one integer, the integer 0, which is the integer corresponding to the column with column ID, record ID. Anyway, these are 4 different ways of specifying the exact same thing, namely this subset of values from the survey's data frame, right? Here it looks a bit different because it's a different type probably, right? Let's see, visually it looks different. This comes out as a data frame, okay. This is returned as a pandas series, yeah. I think the other ones are pandas series as well. Okay, so it depends maybe a little bit about what you want. But the reason both to make you aware of a third syntax option for subsetting, I also wanted to do that, and also just go back again to look at the, if you don't really care about which syntax to use, and then this final syntax, as I showed, gives you a data frame back, so you might want to use that for that reason, depending on what you're going to go on further to do in your processing pipeline. But just to time things again, because if we've got a batch pipeline where you've got loads of this stuff happening, then performance can matter. Just out of interest, let's look at what the timing. It actually shows us that using lock or ilock. Okay, using ilock is the slowest by far. Using lock is about as fast as the case where you first specify the rows out of the survey's data frame and then subsequently subset based on the record ID. But the fastest, again, a factor 6 compared to this approach, although you're also creating a data frame, is the case where you just first of all focus in on the record ID column and then look at the rows, then specify which rows to look at. Now, there could be all kinds of reasons why that's the case, and it's not really a topic of this course, but it could be because of the memory layout of the data frame, in that these data, I can imagine, I don't know for sure, but I can imagine that each individual column, the data in each individual column, may well be laid out contiguously in memory, which means that it will be faster to access. Again, I'm just speculating here. It's how NumPy works. In the end, pandas is based on NumPy, so I wouldn't be surprised. But yeah, I just thought it was interesting. So you have another syntax that maybe is even more intuitive than this ilock and lock-based syntax, and actually is also faster. It shows a lot faster compared to some variations. Okay. Okay. Yeah. Unless anybody had any questions about that challenge, or had any alternative versions that you want to ask about, we can continue on. So far we were choosing a subset of our data based on essentially on indices, on basically saying, whether it's labeled indices or numerical indices. It's just saying, these ranges or these specific entries based on some knowledge I have, which ones I want. Select that subset and give me that back as a data frame or as a pandas series, depending on the syntax. But now the question is, if you don't know exactly which entries you want, clearly, as is often the case, you are interrogating your data and you have some filtering that you're wanting to apply to select a subset on of the data based on one or more criteria. So, for example, if you want to select all the data where all the rows where the value of the year is equal to 2002. And a way to do that, one way to do that, is this single line here. Now, there's actually a lot happening there. So this apparently, okay, let's check it. So we say, I want to copy paste, so surveys, data frame. Give me the result where I'm using, what am I doing? I'm asking it, tell me the entries of surveys data frame indexed by, apparently somehow specified by index surveys data frame itself, dot year equals 2002. And that somehow works, right? So what it's giving me is all these rows where it clearly is the case that the year is 2002. If I looked at the original data, we had other years as well. So clearly it's selected subset. So what's actually going on here? Okay, we'll look at this more later, but basically, if you give you a preview now, it's oops, sorry. Okay, so what is happening? Let's inspect this. Let's interrogate this, right? So it's always just making it concrete. So this thing that we've put here as an argument for indexing our service data frame. Let's just investigate that. So what we specified there was service data frame dot year equals to 2002. Well, service data frame dot year, that's just one of the columns, right? We could have equally said use this syntax. And as always, I can't help it. Let's see what's faster. And let's use that one. Still timing. Okay, right, so I'm gonna use this one. But you know what, I'll stick to the example because it's maybe easier to look back at. So I'll just use a dot here. Anyway, we said the criterion was df.year is equal to 2002. So if I execute that, what do I get? I get, well, let's see, what is the type? Oops. I get a pandas series back. And it's a pandas series which has a series of values that are not the years themselves, but are booleans. So for each row, I get the index and then the value false or true. Now this is effectively a it's telling you for which entries for surveys data frame is it the case that the year is equal to 2002, for which rows is that true. And the way that pandas works is I can specify that as a so-called mask, as a conditional mask because I guess the idea comes from, like, I don't know, lithographic printing or from line drawing, where you basically apply you cut out you've got a mask. So you've got your original data frame, and then you create something, you superimpose on that a filter, and you select where you're going to let through the values and where you're actually going to ignore the values that are there and where you're going to actually select them. And when it's true, you choose the values and you select them, and when it's false, you ignore them. So you don't include them in the result. So that's the way that it's operating. So when we say surveys data frame, selecting this, we're picking all the rows from the data frame where the when the year is 2022. And these kind of conditional statements can be formulated using whatever conditional Boolean operators we want to use. We care to use like equality, inequality, greater than or less than, greater than or equal to, less than or equal to. So we could equivalently select all the rows that do not contain the year 2002, so exclude any that do. So we just simply say use the conditional operator not equal to 2002. And we can combine criteria. We can use the AND operator to combine two criteria. So if we have one criterion here, surveys df.year is greater than or equal to 1980. We'll look at the Boolean mask resulting from that. And then we have another criterion where the year is less than or equal to 1985. And if we take the logical AND of both of those, we can actually, what I'm going to do, let's see if I can, let's see if this makes sense. No, okay. So there's something here which is used in the examples here, which I'm going to show you now, which is something to be aware of, useful, which is that if I want to count how many for how many rows it's true that this condition is satisfied, the way I can do that is I can use a sum, and that makes use of the fact that Python treats the Boolean false as 0 and a Boolean true as 1, definitely for the purposes of the sum operation. So if I were to ask the sum of this, I get essentially I'm counting all I'm counting the number of instances of true. So this tells me how many rows it's true for which it's true that the year is greater than 1980 without any other constraints. This tells me the number of rows for which it's true that the year is less than 1985 without any other constraints. This tells me the number of rows for which it's true that both the years between 1980 and 1985 inclusive of both years. So obviously that's a subset of both of those constraints. And then finally, I'm just combining that as an argument to constrain which entries I return from the data. And there I could ask it. Well, I could ask it for the length, but here you see already that it's told me here when I print it out. It's told me that there are 8,957 rows, which corresponds to this number of. It's just showing that it's consistent. Okay, so here's the challenge here. So here, have a go at using this approach, or whatever you can make work really, to select rows in the survey's data frame that have data from the year 1999 and contain weight values less than or equal to 8. Check how many rows those are. And after that, find all the plots, i.e. find all the site plot IDs, the site IDs, plot IDs, all the sites that contain predictor species in survey data frame. So we'll look at this in, well, take it till quarter two, and have a look at this. Okay, so let's have a quick look at, well, have a look however long we want at this this challenge. So the first bit is select a subset of rows in the data frame that have data from the year 1999 and weight values less than or equal to 8. So it sounds very similar to what we did just above, right? Because kind of it's combining two conditionals, one being one can basically say, okay, year equal to 1999, so year equal to 1999, then and weight less than or equal to 8 can be basically already set what it's written down as. The year field should be equal to 1999, and the weight should be equal to or less than or equal to 8. Use that as an index, and then we should get out a fairly small subset of rows here for which the data satisfies those criteria. And the question is, so how many rows did you end up with? Well, we discussed already that you can use the sum there because of how Python treats true and false. You can also do, let's just take this criterion. So here, this is the set. And if we want to say, oh yeah, okay, so what we can do is, so we could sum that, like I just said, to get the number of entries where that's true, or we can just go ahead and construct, as the line above did, use that criterion to select the data, we get those values, and then if it doesn't really tell us directly what the shape is of that, we can just ask for the, well, we ask for the length, right, which is the number of rows. It's very concretely just asking us to tell it. But if we sum up that criterion, it should give us the same thing, right? So that's true, that's 5. So we can do that, or we can simply use a selection criterion and take the length of the resulting thing. Or like I said, take a look at the shape. So instead of length, instead of calling it the length function, we do dot shape. That'll tell us 5 times 9, 5 rows, 9 columns. Second question is, what it's asking for is this new it's introducing this new syntax, is in. So that's a way to check whether any rows satisfy that particular column, that the field corresponding to a particular column is equal to one or more values enumerated in a list. So, for example, for the case of this data where there's particular species, so it's the sample solution shows essentially just pick a species or pick a couple of species that you care about. So they're identified by these 2-letter IDs. So it's an example given here is two arbitrary species, PB and PL. So we say our selection criterion is whether or not the gives all the rows for which the column species ID, for which the value in the column species ID is in, i.e. is equal to one of the elements of a list, namely the list with the species IDs PB and PL, no idea what those stand for. So that's our selection criterion. Obviously the first 5 and last 5 entries don't have any of these, but there must be some. If we do the sum, we can see how many there are. 2,927 that are either PB or PL. And then it says, find all the plots for which that's true. Okay, so we've got our selection criterion. So this is the logical criterion, and now return the data. PDF. Give us all the data entries. Oops. Give us all the data for which species is either PB or PL. Right, and then what we care about is the plot IDs. So what are, for that data, give us just the integers which correspond to the identifiers of the plot ID. Okay, so we have all of those. Now we've got loads of repetitions, obviously. We say we just care about the unique plots. We don't want a summary. There's only 24 possible plots, as it turns out. So we're going to use the unique function to give us to simplify that list. I think that was used before. I'm not sure, the first episode or second episode potentially. So this just prints out a unique list of all the plot IDs. You could sort them, I guess. So those are the plot IDs for which the species ID PV or PL occurs at least once in the data. And then how many records contain these values? So that is, yeah, okay, that's the shape. Simply, we're not told immediately there, but so there's 24 for which that's true. Again, the third one is, I think, very straightforward. Just create a query that finds all rows with a weight value greater than or equal to 0. I mean, that's kind of simpler than the above. It's simply another option, right? Saying where is this greater, where is the weight value greater than or equal to 0. And then finally, we've got this twiddle or tilde, which we can use to negate, to get the negative, the opposite of the selection, logical negation. So where your criterion returns true, turn around to false and flip false to true. So use that to write a query that selects all the rows where the sex is neither equal to M nor F. So you use the, one way to do it would be to use the isIn with M and F, so that it will give you all the rows. So the criterion without the tilde would be the logical criterion of all the rows where the sex field is either M or F, and then the logical negation of that would be the flip. So it's neither M nor F, and give you all the data selected using that criterion. So you can see the shape immediately here. There's 2,500 rows just over where, yeah, for whatever reason, there's just nans or, yeah, well, whatever it is, whether it's nans or something else, or you know logically that you filtered according to it being not, it's neither M nor F, it's something else. It could be a nan, it could be whatever. Okay. So here's a bit that actually explains what I've already explained, which is taking a bit simpler, sort of explaining the Booleans in Python. So it's going down at an individual level rather than operating on an entire array. Think about individual variables being equal or greater than or so this will return false. This will return true, right? And this is basically telling you that can be done on an overall data frame level. So and that's introducing another function that can be quite useful to detect, as you might often have with data, especially I guess experimental data or well, yeah, possibly stuff you've computed as well. If there's some error or some missing data, there's a function called isNull, which you can use to issue a selection criteria where to test whether the value is null. When isNull is essentially equivalent to is nan, so where it's missing or recorded as nan. And there are some defaults, which I think we'll talk about in another episode, about how your file, your CSV file, when it's read in, Pandas has to make a certain choice about how to decide that entries are marked as nan. So it has some defaults for that. You can also play around with that, but we can look at that later. So here this just shows that if you say pd.isNull, so this is one of these functions that, you know, some function, you might be familiar with programming the concept of an instance function versus a class function, if that means anything to you. It's not a Python thing, but the distinction there is this function isNull. How are you calling it? The way it's written here is it's pd.isNull. PD stands for pandas, because when we started our session, we did import pandas as PD, right? So PD refers to the library as a whole. So then you're saying call this function which exists in the library as a whole. and feed it, give it what piece of data you want to tell us something about. That's like the function doesn't belong to the instance of this data. It's just a function that's there in the library, ready for us to use anytime. What it tells us is it tells you true where the value is null. Now, I don't think this exists. Service df is null. Oh, yeah, actually that exists as well. So that works as well. So either way, I'm not sure if there's any difference in performance. It's probably just an alias to the same thing. So if you don't remember, they both exist. So it depends on what you want to do, what's more convenient. So you can, of course, now that's useful because you can, of course, use this again as a selection criterion to exclude from your data any cases where where there is a nan. So so here it says to select just the rows with nan that do have nan values. Then obviously the opposite is we probably want to exclude it. So we know we can do the negation of that. So anyway, if we want to select the rows where with any nan values, then we say if we were to just use pd.isNull for the entire survey's data frame as our selection criterion, that would apply this entire mask. Now this the any, let's see, the dot any is an interesting point. So let's see if we can get some help on this function. No, so it can be useful. Sometimes it takes a little bit of playing around to find how to get help with this the correct syntax for getting. Here we go. Documentation help on any given function. You can always sort of Google it and look it up online somewhere, but within IPython or Jupyter Notebook, you can often get help by either adding a question mark at the end of a function call or an attribute, or enclosing it within the help brackets. So help for isNull tells you what it does, takes a scalar or array-like object, indicates where the values are missing, it tells you a bit how it interprets it, and there's this any, presumably will tell you about the any option. No, okay, it doesn't. Okay, that's not great documentation then. We'll just apply what it says. So we'll say, let's look at that criterion. Right. So here we're applying so we're saying any x is 1. This is essentially, I think, saying that determine here the logical criterion is select the rows where it's true that where it's the case that any of the columns, one or more of the columns have a nan. But that's what that's saying. And so then select our data. So now we've selected the data where that's true, where that's the case. So these are values where there's a nan in one or more columns. So those are 4,837 rows. Probably, we might like to only keep our data where there's no nans anywhere. So then you just put this tilde in for the negation, right? That's all the remainder says, over 30,000 rows. Okay, I realize it's just 3 o'clock now. So let's just have a quick look at what it says here. The any method just explained. The next episode says more about that. You can try running isNull in a particular column to check that out. So there essentially you're asking for whether there's a nan in any particular column, right? And basing a logical criterion on whether it's null in any particular column rather than in one or more columns, without regard to which column. So why don't you take, so there's a break until 1:15. So after the break, we will have a quick look at this final challenge, and then start off with the next episode. Okay. So let's have a good look at this challenge. How people got on. So the question is, create a new data frame that only contains rows from data where the sex value is where sex value is marked as neither female nor male. Think of the number of rows and check that it's true, that makes sense. So we'll essentially just look through this solution and just talk through the logic of this approach. There's always, often more than one way to do it. Let's just think about the way that's done here. So what we want is a selection criteria where it's the case that the values in the survey's data frame, that the value for the column 6 is is neither M nor F, and we already, I think, previously talked about one way to do that is to say that it is one of those values and then negate that. So M or F, and yes, isn't function called. You give it a list, M or F. So if I do that without negation, I get lots of entries. And now I do the negation. Oops, negation of that condition. So that's fewer entries probably. I mean, again, the shape. No, we have to sum it to actually find out how many cases it's okay. 2,511. Yeah, that's the same thing we saw before. Okay, so that's our selection criterion. Now we want to actually get the values from the data frame where that selection criterion is true. So we provided as an input argument for indexing into that data frame. Okay, so there's 2,500 rows of data that we get out. And the question says, create a new data frame that only contains those values. So we're going to create, this is a new suggestion. There is the hint that says you could take a copy, say non-MF surveys data frame equals copy of that. Okay. Well, we already know how many entries there are. We just looked at the sum to be equivalent to the length of that new data frame. So just to check, just to confirm that, oops, that dot shape, yeah, 2,511. Okay, verify by comparing the number of rows in the data frame with the number of rows in the survey data frame where sex says no. Yeah, we already did that. Okay, then part 2, question 2. Create a new data frame that contains only observations that are sex male or female, or that are sex male or female. So surveys data frame where it is the case that surveys data frame sex is in the set consisting of either M or F. So we don't take negation here. We just take it as is. Oh, but that's not the only criterion. We also have an and the criterion that the weight. So in other words, survey data frame column weight is strictly greater than 0. Okay, that's our selection criterion. Put that in parentheses to open my parentheses here. So that's the first logical criterion, and there's an Boolean and the second logical criterion, and those together form the selection index. Okay, clearly missing something. So that matches that. What I missed? Oh, here we go. Yeah, that first parenthesis was a closing bracket for the is-in call. Okay, it's behaving a bit oddly. Okay, so that's extracted all the values where the weight is greater than 0, or where the sex is either M or F. So then from that, create a stacked bar plot of average weight by plot, i.e. by plot ID by site. The male and female values stacked for each plot. Okay, so I'm gonna have to do kind of grouping, like we did before. The thing I want to plot, the thing I want to compute is the weight. It's a logical grouping. So I'm going to take that thing I've just constructed and say, let's say grouped. Okay, I'm going to say that dot group. The thing I've just constructed dot group by group by the fields sex and plot ID. So I've got two grouping, two-level grouping. Oops, plot ID and sex. So that is itself okay. Of course, don't get anything out. So I would just check what I get. Oh, I need to. So that's just a grouping of the data, logical grouping by plot ID and sex. Then, of course, is all the different values other than the plot ID and sex, which I've got in that, which accessible and compute, and I can compute aggregate statistics for. But the one that I want in particular is the weight. So the thing I care about is the weight. And for that, I can compute dot mean. Okay, so this looks like it's taking a slightly different approach from the approach here. Criterion is here, and then they select the sex, weight, and plot ID, and only then do the grouping by. Oh, okay. So here in this approach, they've applied the same logical criterion, but then they've extracted, they've created a data frame that contains just sex, weight, and plot ID, and then done a grouping on that. Yeah, okay, this is one more step, I think. Well, it also works. I don't know if the performance might be slightly more or not. Maybe not, because you're creating an additional intermediary. But hopefully this is clear, and I'm going to just stick with this. You could subdivide this into two lines for clarity, right? With the initial construct, I could say here the I could call it MF non-zero weights as a variable name. Define that as my subset of the full service data frame, and then say MF non-zero weights dot group by plot ID sex. So I'm going to say the mean weights by plot and sex. So just giving it a variable name to store that as an intermediate result to be a little bit more explicit. So like we had before, that is we need to. It's a two-level thing. In order to plot that, we need to unstack it, get those two columns into two columns and rows. So we do unstack. That will look amenable to being plotted as a stacked bar plot. So final call for that will be to take that unstacked thing and do plot kind equals bar and stacked equals true, like we did before. Let's see if that works. Yep, that works. Okay. They've not included it's not like they've included the actual plot here. But yeah, that tells us for each plot ID the average weight stacked for both the sexes. Okay, so the point of this episode was different ways of selecting subsets of your data and plotting it, both based on explicit indices, labels, numerical indices, and labeled indices, or based on all kinds of selection criteria that you might like to apply, a logical combination of those selection criteria, which, as we saw, are implemented as masks that tell pandas which values to extract from the initial data frame. Okay, so we talked indices, slices, column headings, condition-based subsetting. We talked about how to take care that your ranges are correct with regards to zero indexing and exclusion and inclusion. And remember the three options you've got with iLock, lock, and the straightforward square parentheses, which can take multi-dimensional listing. Right, so that's that episode. Unless there's any more questions, we'll make a start on the next episode. We may not finish it before the end of the session at 1:15, but we'll see how we go, and then we continue tomorrow. So, episode 5, data types and formats. So I will just start a new kernel for that. Okay, so this is basically about dealing with data types, and a lot of this will be about numerical types, integers and floating points, and also dealing with missing and null values, nands, not a number, like mentioned, we came across already a bit before. So it's basically trying to give you some background to understand what's going on when you're reading in CSV data, for example, from a file, and also when you're doing numerical operations, and how these things, how data is actually represented numerically by Python and by pandas in particular. So essentially, mathematically, what we've got floating point numbers or real numbers, which are stored in primitive data types called floats. And we've got integers, which are stored in primitive data type called ints. Then we've got the general data type in Python, which is an object, and everything in Python is an object. There's no other, it's a top level, kind of simplest case. So in pandas, you've got objects. You've got int64 type for 64-bit integers. Just says how much memory you've got available, the range of integers you can represent, smallest and largest value, and 64-bit floating point numbers, which again tells you about the maximum number of the highest precision number of significant figures you can store. And then we have another data type that we won't get into in this episode anyway, this session, which is the date time data type. So there's some links here for additional material on that. Okay, let's have a look. Let's just load our original data again. Again, it's just the same CSV file as before. So this is reminding us of types more generally, which I've been already using a few times this afternoon. It's useful occasionally to just check what the type is of something, because with Python is a very flexible language. You can kind of do or try to do anything, and it will often do sensible things. But to understand, it's useful to understand what the objects are that you're actually getting out. Because often, for me anyway, if I'm dealing with some, if I'm trying to make something work, whether it's using pandas or whatever library that I'm not familiar with yet, whatever Python library I'm not familiar with, I typically just try something, a simple starting point, and then once you do something like, for example, in this case, read in something using what looks like the right thing to do to read in some CSV data, then you see, well, okay, what have I got now? What can I actually work with? So in other words, what is this variable that I've got? So that's why they suggest that you check the type, surveys, df. We already know it's a data frame, but again, this confirms that. And that tells you something about the kinds of operations you can do with it, from it, to it, etc. So if you just start typing the variable name itself and do dot, and then try to tab complete, pressing tab once, you'll get a long list of potential attributes and functions. So that gives you options to go off. So you can just do question mark as well, which tells you something about data frames. It tells you something about the parameters, about functionality as well. So that's just useful to be aware of, know what you're dealing with. And when it comes to the data frame created by reading in the CSV file, we can look at an attribute. It's called, let's see, dtype. Type complete, yes, dtypes. So the example given here looks at the dtype, which is short for data type, for a particular field, particular column, text. But let's just call .dtypes attributes, or inspect the .dtypes attribute for the entire data frame, which tells us the numerical data types, or whatever data types are for all of the columns. So we see for a lot of these, it's integers, int64. So these two is object, and for these it's floats. Now, why is this though? Pandas is basically at the point when it read in the CSV file, it used some heuristics to basically detect, oh, what do I think is an integer? What do I think is a float? And basically comes down to whether if it's a numerical value, if there's no decimal point, no value after the decimal point, then assume it's an integer and store it as an integer. And if it's got a decimal point, then store it as a floating point object, as a float64. And if it's neither, if it's not identifiable either as numerical, straightforwardly, then just store it as an object, an abstract object. And pandas, that refers to string text. So yeah, that's just okay, here we go. That's just summarizing the thing, same thing. So some information about integers and floats. This is just stuff that you may already be familiar with in general in Python, maybe not, but it's useful just to be aware of. It's kind of just highlighting the kind of operations, how Python does operations with integers and floats. If you divide one integer by another, you get a float, at least in Python 3. Just be aware of that. So if you say 5 divided by 9, so it's a type 5, an int type 9, int type of 5 divided by 9 is a float. And that's this Python itself rather than pandas. So pandas would store it as a float 64 rather than just a float. It's ultimately the same thing. So you can convert types to one another to some extent. So the example given here is if you initialize something as a float, you can cast it as an int, which just rounds down to Python by default, rounds that down and just discards the figures after the decimal point. And likewise, you can convert an integer to a float. So Python will assume that b being is equal to 7 is implicitly an integer. It will start as such, and then you can cast it as a float using this function call. Okay, so going back to the data, there are ways of casting all the data for a particular column from one type to another. So the example given here is where you convert all the values for the record ID column to type float64, and then check that is the case. So return that is the case. So the thing to try, if you try, is convert the plot ID column to floats. and then try this thing. So just I'll just say nothing for a minute and come back and we can have a look at that so you can have a go yourself. Okay, so I guess people have tried that probably. So presumably you were able to do this first conversion, converting the plot ID to float, and that just that just converts values, integer values, to float points with 0 behind the decimal point. Then trying to do the opposite for the weight column, so converting to casting as type integer the survey's data frame plot weight values. So what goes wrong here is not what you might expect, i.e. if there is a floating point value stored, if there's a numerical floating point value stored for the weight, Python is happy in principle to just cast that into an integer and by discarding the figures behind the decimal point. But what it complains about will be some cases like this, where it says int casting nan error cannot convert non-finite values nan and a not a number nan or infinite to integer. So basically, if the column any values that are not numerical within a column, it will complain about not being able to cast because there's no defined, not numerical to begin with. So there's no defined way of, if it's not already a floating point number, then it's definitely not going to be an int number anyway. Not going to be an int number either. So this comes out to nans, which we've come a few times already. So this is something to just look at how pandas deals with nans. So so far they've come up once or twice, and we've looked at how to selectively exclude nans, how to exclude data from our data frame where one or more columns has a nan, or where a particular column has a nan. But let's look a bit more about the role these play and how they are, why they're actually useful to have there. So pandas will have some heuristics about how to classify something as a nan when it reads in a CSV file. It has some default, which is, for example, that if it finds no value, like by default, put a nan there. If other values in the column are numerical. So one question you might immediately ask yourself is, well, so far we were doing things like if you had our survey's data frame, like it says there, if you said, okay, for the weight, those are all the weights, you can already see some nans popping up there. Give me some aggregate statistics, like, for example, the mean. Compute the mean. So you might be surprised to say, okay, well, hang on a second. So if there's nans there, what happens to those cases? So Python pandas just skips over those entries. So those entries don't count in computing the mean. Of course, how could they? Because they're not numerical. So the choice is either you would either have to throw an error or simply ignore them, and by default it ignores them. Of course, that means that the mean that you're computing might not necessarily biased. Well, it could be biased in the sense that if there is a bias, if there is an underlying bias in what are the missing values, then you could mistakenly be thinking that the mean represents the genuine. Anyway, you know what I mean, it like represents the genuine data, whereas actually represents a subset of the data where there are values. So the point is that you need to be aware that this is happening. Be aware what's happening at the stage where you read input data. Be aware what's happening at the stage where you compute where you select a subset of your data. Be aware what's happening when you compute anything, aggregate statistics or whatever else, or any other logical computations, numerical computations based on the data. So be aware of whether there are any nans and how you're including or excluding them, and how they are contributing or not to any computations that you might do. So Yeah, there's some, and it depends on your field. For example, like you gives an example like remote sensing. There's lots of sensors take like, they have some, rather than just giving not recording a value at all. When there's some data missing, they record some value that's a placeholder for, something went wrong, or I don't have any data, which is something like minus 99999 or something like that. Obviously, if when you read your input data, those values are simply taken across as minus 99999, without anything being amiss, and you're not aware of that. If you're computing a mean and it incorporates those values as numerical values that contribute to the computation of the mean, then you've got a problem. Well, obviously you're not genuinely computing and you're incorporating non-measured values into your calculation. So you have choice at read time, when you're reading, to tell, for example, pandas what are the kind of values to consider as nans. So you could specify the particular choice of, say, you could tell pandas, this is in my case, in my input data, this corresponds to a nan, so mark it as such, so that when you read it in and you compute any statistics, then they will simply be left out rather than distorting the computed values. Right, so here's an example where we're saying, okay, so there's a function very conveniently which is called is_n. Is_n is not a number. So you could ask for we just looked at a case where we looked at the weight. We saw that there logical criterion. So basically, we saw that there were a bunch of nans there, and if we want to exclude data where the weight is nan, then we can form a logical selection criteria where we say service data frame weight dot is an a. Yeah, so we get some trues and false corresponding to where the weight is not a number. We can use that as a selection criterion for our data frame, so that we only incorporate values where, at the moment we only incorporate values where the weight is a nan. So we might want, the negation of that, where it's not a nan. So where there is a genuine weight value there. Yeah, and okay, the length will tell you how many rows are that correspond to that. So you can do things to modify selectively all instances where your data is by using the fill NA method. Suggest making a copy of the data so you don't lose your work. Okay, that's up to you. I mean, we can do it here, but so let's do that. So we create a new data frame with an explicit copy. New data frame is a copy of the old data frame, service data frame, and there we assign. Well, first of all, let's just see what that does. So we say all those weight entries fill not number with the value 0 instead. So what do we get? We get cases where wherever there was a nan, it's now 0. Wherever it's not a nan, wherever it wasn't a nan, we have the original weight. So we can assign that output to replace the entire column of our data frame, of our copied data frame. Okay, so now if we ask the question of what is, well, it says here, what is the mean of that? Obviously, it's going to be less. It's 38 compared to 42 before. That's obvious because we've, rather than these values being excluded, they are now included as genuinely in our computation for 0, as being 0. That may or may not be the right thing to do, right, depending on what the data actually corresponds to. But that's up to you. This just gives you tools to do whatever's the right thing for your particular data. So making conscious decisions about that. Okay, so just for this challenge, just to take a minute to try out this challenge. We'll come back to that. Okay, so maybe we've had a chance to try that out. So as usual, there's more than one way to do it. Because the question is, count the number of missing values per column. So, i.e. the number of NANDs per column. So we've got our data frame. For each column, there will be maybe different numbers of NANDs, because it could be the case that the weight was recorded just fine, but the hind foot length wasn't recorded, or the other way around, or both. So there'll be different numbers of NANDs for each column. Count how many there are for each column, and it's giving a hint, saying you can use a method function call .count, and it tells you. I think we used .count before in one of the earlier episodes, possibly. What it gives you is the number of non-NaN observations per column. Also suggests try looking to the is_NA method. So there's a solution here, which you can look at in a minute. So I think the solution that I had in mind was possibly a little bit simpler. So first of all, let's look at this count, this idea of counting. So if we do surveys data frame simply count. So that tells us for each column how many non-NaN observations there are. So we see that for these columns, plot ID, year, day, month, record ID, there are the same number. All the values. This is the total length of the data frame. Actually, all these values are not non-NaN, not a number. So they are numbers, or they are at least not missing values. And the other columns, they all have a number of non-NaNs, number of a smaller number of this is missing, and the difference, essentially, the number of missing values per column is essentially this total 35549, which is the length of the data frame, minus each of the values for each of the successive values. So one way to actually do that is to say, use a little bit of overloading, which is, well, I can just get what is that value, number of surveys, length of the, I can do it all manually, but so that 35549 is, and 35549 is the length of the survey data frame. What I can do is I can actually just subtract from that the thing we have above, so the count. And the nice thing what that does is the arithmetical, it'll perform the arithmetical operation. So this scroll is not really working in web browser for some reason. So to perform the arithmetical operation of subtracting from that scalar single value 3559 each of those values for the individual columns. So that tells you directly the number of missing values for each column. The solution given here is a little bit more convoluted. I mean, it involves a for loop, or an iterator, I should say. So it iterating explicitly over the columns. Just a little bit less elegant, but and then printing out, checking for each column, is NA the selection criterion of is this column not a number? Is the value of the column not a number? Selecting all the columns for which that is the case. Sorry, selecting all the rows for which that column is not a number. That's finding the length of that. So that, sorry, it's not where it's not number, it's where it is not a number. So it's directly computing the number of missing values rather than finding the numbers where it is not missing and then subtracting them. So this isn't actually using the count, right? So it's suggested using is NA instead of count. So I've used count, and this is using is NA. But obviously, there's more than one way of doing it, and you could time it to see how to do it. And is noticing is non, is NA are equivalent, and they behave identically, just in case you're wondering. Okay. Anyway, if anybody had any other approach for doing it, feel free to share, and we can look at that. So I think the final bit of this episode is a bit about writing out data to CSV. So I mean, that's not related to data types so much. It's a very general thing, but it's basically you've got the option where so you've got your nans. You might want to get rid of the rows that contain missing values. So the command drop NA allows you to do that. So if we take our original data frame, let's drop NA. Let me use a question mark there to see what that amounts to. So let's see what that says. Drop NA. Okay, remove missing values. Okay, so options here. Rows or columns which missing values are removed. The default is rows. Returns data frame with the nan entries dropped from it. So you have some options there to play around with. Let's do it. Okay, so that has fewer rows, about 5,000 rows less. df NA equals that. Yeah, and then closing the loop after we've done some data processing. We started off with read CSV. Now I've got to CSV to export, to write out the data frame to CSV rather than reading it as a CSV and getting it as a data frame. So we can just write that out, saying df NA dot to CSV out dot CSV, and that should there's an option here that you can use. Okay, let's look. Let me see if some magic works. So I'm going to use the ls command. Ls is of course not Python. Ls is bash shell or terminal command, which IPython and Jupyter Kernel Notebook recognize as a magic command. So that gives me here immediately the contents of the directory I'm in. So the out.csv file has been created. Now I don't think this cat works actually. I can't remember. Yeah, it works. Okay, so it recognizes cat. So you can see there what's you can see the labels, right? The column labels and the values. I think what this is talking about here is index equals false. Let's see if we write out the data again, but this time with the option index equals false. So let's look at the difference. Okay, so I think the default was already that it was false. So it may have changed compared to this version of pandas that is written for. But yeah. So to recap, we've looked at essentially this was about just being aware of some of the issues surrounding representation and operation with numerical data types when you read data into using pandas from a CSV file. So you could have a look actually at what's useful to look at your leisure is to look at pandas.read CSV, to look at the documentation for that. So you'll see here that you've got options. So you've got various options, for example, delimiter. So sometimes your CSV file, the C in CSV stands for comma separated values, so values separated by commas. Sometimes the delimiter is not a comma, but it's something else. It could be an arbitrary string that you can specify, or it could be, you have some options there. And you've also got the option of specifying what to consider as NaN values. And I think actually the next episode gets you to choose some of this. So you've got a lot of options. So you've got options when it comes to reading in the data. Then you've got you should be aware of NaNs and how they're make sure that what you intend to be a NaN computation is in fact read in as NaN, or if not, then change it manually as part of your processing pipeline before you compute and visualize anything. Then, yeah, when you write out CSV, you again should consider if you're dropping any data where there are NaNs. we showed at the time that you've got options when it comes to 2CSV as well. Okay, so we've got about 15 minutes left until the planned finish time of today, which we can use to make a quick start on the next episode. So tomorrow morning we will continue that, but we can start unless anybody has any questions on this episode. Feel free to ask. Okay, yeah, thanks, Luke. Okay, so I will start just another notebook for this episode. 6, combining, joining, workbook. Okay, so the idea with this episode is basically to take a the next step is that you've maybe got, you need to do a little bit more sophisticated things with data frames. You might have several files. You might need to combine data from multiple files. You might want to, so the example that's given in this episode is having 2 data frames where the second data frame is essentially a lookup table for a set of values that a limited set of enumerated values. Like the example is about species. So you can imagine where you have information relating to all kinds of properties to do with a particular species ID. A particular species is stored by recording a particular, like, 2-letter species ID in the examples here. And each species ID has its own, life cycle data, all kinds of stuff, right? In your first data frame, the surveys data frame that we've been looking at so far, in principle, you could always store, for each recording, you could store all that additional information that depends on the species. But really, you'd just be duplicating a lot of data, because as soon as you know that what the species ID is, all the other data is just might follow directly from that. So it's kind of superfluous to replicate, the bunch of data. So you might have 2 data frames, one where the survey data is stored and records the species ID. You might have another data frame that stores for each species ID a bunch of other data, and then you'll be flexibly able to reduce your overall storage size by not replicating the data for any given species every time that species appears in a row in the first data frame. But still, you've got the flexibility to use the to filter, compute, or anything, visualize aspects of the that link the survey data to the species-specific data in the second data frame. And you can just imagine all kinds of contexts where it's useful to be able to do that. So where you're somehow combining the information from 2 data frames, using something that connects them, which is kind of like a key, unique ID that links the 2 together. So-called join key is a good example. So there's various ways of doing this. We start off by reading in our data as before. Now there is an explicit specification of some of the options that I mentioned just in the last episode, which we haven't specified so far. I think it doesn't actually make a difference. So if I just do surveys, okay. I've not imported pandas, obviously. that's surveys df. And now I'm going to do what it says in the notes here. Read it in with these additional options. Split across the line just for readability, but I'm going to just keep it like this. So this is specifying the additional options. Keep default NA equals false. So it's saying check out, check out the specific NA values, NaN values. What do I assign as a NaN? Something that's here that's missing. Now I think that actually is unnecessary. Let me say NA spec. I'll just. Now I think those are the two. Those are the same. Those end the same thing because I think it actually is explicitly specifying what's already a default. So I'm going to do a check for that. I think this will work. Yes. Okay. So of course that's giving me a conditional that. That's just a good example, right? So this is okay. I need to do an overall check for whether this amount, whether this is true everywhere, whether it's okay. So not it's false for it's false for the weights. Okay. So there is a difference there. Okay. Let's have a quick look at that. Okay, so in the first case, that's NaNs for the weights. Okay, but there are also NaNs here, so I don't know exactly what's going on there. Anyway, we'll just do what it says. Again, I think those are those defaults. I think those are the defaults anyway. Do what it says, and call that surveys df. Okay. So we've got a surveys. That's what we had before already. Now we have another data file, our species. So this is exactly what I was talking about just now. So let me just read this in. It's using the same syntax, same options, but now the data file is species.csv. And I'm going to call that species df data file. Data frame. Right, so surveys we're already familiar with. We can just again look at it. Just print out the head. And species df. I'm actually going to print out the entire thing because it's not that long. It's not 35,000 rows. It's just 53 rows. So this is a canonical list of for each species ID. You see each species ID only appears once in this list. So there are 53 possible species, well, that we've got record of anyway, information about, and taxonomical. Okay, I don't know anything about this stuff. So anyway, taxonomy information like genus, species, and taxa. Right? So it's got additional information for each species, like I already hinted at before. Here it explains the additional options that were used for read CSV, which we didn't use previously. So you can have a look at the documentation to clarify this. So here this amounts to explicitly requesting that empty values in the CSV are recorded as NaNs. But yeah, like it says, this is, however, also the default behavior of read CSV. So there's a link here if you want more information about that. And this may just be the this is in fact just the I think just the documentation that I brought up and I used question mark or help in the kernel in the IPython Jupyter notebook. Okay, so the next step will be to combine to concatenate data. Just a little bit hesitant to start that now because if we start now, it probably won't finish at 1/4 past. Let's have a look. Yeah, let's leave it there. Let's look at it afresh tomorrow morning when we start again. So you have the setup now. You have the context of this. You've got the idea of the two data files, and then we'll look at concatenation, various ways of combining information from two data frames starting tomorrow. What else have we got tomorrow? We've got the other sessions are, let's see. Yes, we have this session of combining data frames with pandas, data workflows and automation, and then plots with plot9 for more advanced visualization. This, just an advanced warning, this SQLite database is using Python and pandas. We will not be covering that tomorrow. So all the resources are there to look at yourself once we get to that, if you want to have a look at that. But I'm sorry to disappoint you if anybody chose to do the course specifically so they could get to SQL databases using Python and pandas to plot data from there. But we won't be covering that. It's kind of beyond the scope we consider it in terms of typical usage that people are interested in. But all the information is there, right? All the guidance is there, the practical is there. Feel free to, of course, ask us about it afterwards. You can contact the help desk or email us if you have any questions. But just a heads up that, though I expect we'll cover, get towards at least start off with start doing this episode and possibly get towards the end of it, depending on time, with plot9 or matplotlib and pandas. We won't do the SQL bit. Okay, so let me just check for the yeah, so something that's, I think I've used it a few times today already, and I think it's just a nice thing to sometimes do if you're doing anything in Python, to use this time it to guide your choices. If it's all the same, to see what's more performant. If you've got more one way of doing it, do the way that is kind of faster, especially if it's something you do often or intensively. So I think we'll leave it there for today. I'll see everybody tomorrow at 9:30. But if there's any questions, yeah, just let me know. Okay, great. See you tomorrow.